I want to teach you the mechanisms, why we see electrical signals with electrodes that are placed on the skin. And you're going to see this in the lab on Thursday or Friday. We're going to record ECG recordings from classmates. As a way to start, let's just remember the path of electrical information. Remember, we're talking about electrical information, not pressure or contraction here, because the ECG is recording electrical information. Pacemaker, action tension. Atrial muscle follows. AV node follows and delays. Bundle of His, bundle of branches, so bundle of His, bundle branches, Purkinje fibers, fast. Fast action potentials, fast conduction, because of there are lots and lots of connection between them. Getting to ventricular muscle, fast. Contraction, and then repolarization. You'll notice that, so now we're going to get into the electrocardiogram. I'm going to start to use the jargon of electrocardiograms, the language of electrocardiography. The P wave, P as in Peter, the P wave is associated with atrial contraction. The spike, which we won't call a spike anymore because we're going to call it a QRS complex. QRS complex is associated with ventricular contraction. The onset of ventricular excitation. And the T wave, T as in Thomas, is associated with the repolarization of the ventricles. Now, some of you students might be wondering, wait a second, so if we see a signal that's associated with the onset of depolarization in atria, why don't we see a signal that is associated with the repolarization in atria? And the answer is it's buried in the depolarization signal from ventricles. So, P wave, depolarization of atria, QRS complex, depolarization of ventricles, T wave, repolarization of ventricles. Now let's break it down. Here is an electrocardiogram that might be recorded in the hospital. You are going to work with this exact signal recording on the problem set. But here's what you see, what you should see. The names of electrodes that are used to record the signals. So you'll see we have some redundancy built into the system. So we're going to have an electrode 1, and an electrode 2, and an electrode 3, and an ADR, and an ADL, and an ADF, and V1, 2, 3, V4, 5, 6. So this is 12 different electrode connections, all recording the same heartbeat. And why do we do 12? Because the redundancy provides physicians with additional information that one electrode would not do. In the ambulance, when they hook up an electrocardiogram, they don't do 12, they just do 1. In the lab, we're going to do 3, because we don't have that ability to do all 12. But in the hospital, when they want to get the most information, they connect all 12. This down here is called the rhythm strip, because it's just one lead recording the whole thing. So this is all recording the same time. This strip is all of this is recording at the same time. So this QRS complex, and this QRS complex, and this one, are all from the very same heartbeat. And this one, this one, this one, and this one are all recorded from the same heartbeat. And now, okay, this one, this one, this one, and this one were the same heartbeat. And now the machine clicked and it changed. And that little glitch right there, that little glitch right there, there's a little spike there. Those are the artifacts of making the switch from 1 to AVR, from 2 to AVL. You don't see the glitch down here because there's no switch. I'm giving you some of this technical information for the problem set. Question, yeah?
Is there one that's more accurate? Because you said like they're in the ambulance only.
You will see that lead 2 is the, if you only were able to connect one lead, like in the ambulance, you would connect lead 2. Lead 2 typically gives you the most information. But in the hospital, we want the real most information, and so we connect all 12. But some of you may be EMTs, and if you did an ECG in the EMT, you're connecting lead 2 probably. Yeah?
These all have certain spots on the body? Like
Yes, you'll see different spots on the body are how we determine which lead is which. That's exactly right. CJ?
So, what makes the amplitudes different between each?
You'll see. I will answer that question. Other questions? So, P wave, QRS complex, P wave, QRS complex, T wave. Just the language. Let's not worry too much about, well, no, you'll need this for the problem set. The distance in time between two of the dark lines is 1/5 of a second. So 5 dark lines, 1, 2, 3, 4, 5, let's say, is 1 second. But we're not going to pay too much attention to the faint lines until lab. Dark lines, 1/5 of a second. And let's not worry about the scale, the vertical scale. Oh, in lab, we will also be talking about a PR segment and an ST segment. But we'll do that in lab. Okay, now we're getting to Evan's question about where on the body we're connected. And we're going to work our way to answering CJ's question about why they're different in different electrodes. So lead 1 is connected, let's not worry about negative and positive. One of the electrodes is connected to the right arm, and the other is connected to the left arm. That connection from right arm to left arm defines an orientation in the body across the chest, like this red arrow. Because this arm is, so the only way to get electricity from here to here is this way. And that defines an orientation, horizontal orientation. Lead 2, one lead is connected to the right arm, and the other lead is connected to the left leg. Right arm, left leg. The only way to get electricity from the right arm to the left leg is this way, so it defines this orientation in the chest. Lead 3, left arm, left leg. Left arm, left leg defines an orientation like this in the chest. So you can see we're building a set of directions. Let's just say we're looking at somebody's chest, anterior surface of the chest. lead 1 is defined by this orientation. Lead 2 is defined by this orientation. And lead 3 is defined by this orientation. Or the other way around. Lead 1 defines this orientation. Lead 2 defines this direction or orientation. Lead 3 defines this orientation. Okay? So we're 3/12 of the way through these connections. The A, so here are 3 more. A stands for augmented, I won't test you on that. V stands for ventricular, I won't test you on that. But I do want you to know AVR, AVL, AVF. The augmented leads, AVR, AVL, and AVF, do a funny thing with the electronics. So one lead is on the right arm, so in AVR, one lead is on the right arm, and the other lead is an average between the left arm and the left leg. That's what this is supposed to illustrate. And so it defines an orientation like this. So AVR is over here. AVL, left arm, and an average of the, left arm and the average of the right arm and the left leg. So AVL defines an orientation like this. And AVF defines an orientation like this. I think you are going to want to memorize this. You do not need to memorize which lead is which. You need to memorize which lead defines which direction. The directions are important. The connections come automatically. If you go to nursing school, you will definitely have to memorize which lead is connected to which arm and which leg and elsewhere. And in medical school, you probably have to memorize it too. But for now, let's just memorize the directions. Okay, so we're 6/12 of the way through. The V leads, V1 through V6, are called the precordial leads, and they are connected around the chest from sternum to axial line. And I am not going to, we don't need to know this. I'm not going to test you on where V1 is and where V6 is. I'm not going to test you on this. But just so you know, the precordial leads are connected across the chest. So, Evan, I don't know, have you had a 12-lead ECG recorded? Okay. So when they connect you for a 12-lead ECG, they connect limb leads, arm, leg, and precordial leads. Sometimes they don't need the precordial leads, and they'll only connect the limb leads, arm, leg, and that's what you're going to be doing in the lab. Sometimes they don't have time for even all the limb leads, and they just connect lead 2, and that's what they do in the ambulance. So these are the other leads. They record information around the chest. So the limb leads record information that is in this plane, and the precordial leads kind of gather information in this plane. And you can see what we're doing. We're gathering 3-dimensional information. One plane, 2 planes defines a volume, and these leads define those planes. Now, let's put this together. Why does a heartbeat generate signals? Why does a heartbeat generate signals like this? Okay, that's what we're doing now. So this is a cartoon of a snapshot. The pink is supposed to illustrate that the SA node has fired an action potential and is depolarized, and the rest of the heart is not yet depolarized. So the spread of depolarization from the SA node throughout the atria generates a signal. That signal comes from the spread of depolarization. That spread of depolarization has an amplitude and it has a direction. What else? What do you know that from physics? What do we call the things in physics that have an amplitude and a direction? A vector. So this spread generates a vector of electrical activity with an amplitude and a direction. And so you can see that, well, let me go to the next slide. If the vector of the signal is aligned with the vector of the lead, we get a positive signal. We can detect a positive signal. If the vector is perpendicular to the direction of the lead is blind to that signal. The signal still exists, but the lead can't see it. And if the vector is oblique to the lead, it sees it, but it only sees part of it. It only sees the part that is parallel to it. So now I'm starting to say, why do we do 12? We do 12 because sometimes leads are blind. And we don't want to be, we want to gather all the information we can. And so we do multiple leads in order to minimize the blindness from one lead. By blind, it can't detect it. Okay? So if the vector is opposite, anti-parallel to the direction of the lead, we get a negative signal. If the vector is oblique, but sort of negative, we get a smaller negative signal. And of course, if there's no signal, there's nothing detected. But you notice there's two ways to get nothing detected. Either no signal or a perpendicular signal. Yes?
Why do we need to know this? Like, what's...
Why do you need to know this?
Yeah, what questions could we add?
It'll be on the problem set.
Even when it's perpendicular, when it's like not correct.
So, now we're going to put this together and understand the electrocardiogram. The first signal that the electrocardiogram detects is the spread of depolarization from the SA node throughout the atrium. That spread has an amplitude, and it has a sort of time-averaged direction. So it generates a vector, and that vector has an amplitude and a direction. So first question, let's get some conversation going here. Why does the ECG not detect the depolarization of the SA node, the SA node itself?
Is it because it's not a vector, because it has no direction?
Kind of, but that's not the simplest answer.
It's like a point where the depolarization actually begins, so.
Yeah, it's where it actually begins. So that's true, it's where it begins. It doesn't actually have a vector. Why? Because it's so small. Things that are small don't have, can't define something that we can detect. Remember, these leads are on the surface of the skin, and the heart is deep in the chest. we're detecting signals on the skin based on things that are happening deep in the chest. We're only being able to detect big things. Little things disappear into the noise. So the SA node depolarization is too small to detect, but the spread of depolarization throughout the atria is big enough to detect, and it generates the P wave, which is actually a pretty small signal, but we can detect. This signal generates amplitude and a direction. It is partially aligned with lead 1, so we get a positive signal. It is partially aligned with lead AVF, so we get a positive signal. Which lead, if this is the cartoon, which lead is the P wave going to be biggest? Lead 2. Why?
Because they're going in the same direction. That's gonna be more parallel.
It's parallel to lead 2. Lead 2 is most closely aligned with this vector. Which lead would give a negative P wave? Lead 3. How many agree with lead 3? Would lead 3 give a negative P wave if this is the orientation? I don't think so. Which lead? What would it be in lead 3? Lead 3 is almost perpendicular to this vector, so it might be vanishingly small in lead 3, too small to detect in lead 3. We might not see a P wave in lead 3. There's still atrial contraction going on, but lead 3 cannot detect it in this cartoon. Which lead is going to give a negative P wave? Sophie?
Lead 1.
Lead 1? No, lead 1 gives a positive P wave.
Oh.
Right there. Lead AVR. Lead AVR is anti-parallel to this vector. So P wave would be negative in AVR. So let's go through them. So here is the vector. Let me draw the vector. I'm going to draw the vector like this. So there's the vector of atrial depolarization. It's partially aligned with lead 1, positive. It's well aligned with lead 2, bigger positive. It's partially aligned with AVF. Maybe the same as lead 1, but smaller than lead 2. It's pretty close to perpendicular, maybe a little negative in lead 3, but close to perpendicular, negative. Is that clear now? Why? So now you can see why there's going to be different amplitudes measured in the different electrodes. And that gives us information about the direction. Let me go on, and we'll use this again for some more. These illustrations are just using 1 and AVF, but I'll quiz you with the other leads. So what happens in the heart after atrial depolarization? What's the next step? Yes, the action potential spread into the atrioventricular node. Can we detect spread through the AV node? No. Why? Too small. Too small, too slow. So once the spread gets into the AV node, the signal gets too small to see, and it goes back to baseline. Goes to 0. So spread and now invisible. What's next?
So the action potential spreads to the pendular phase?
The action potential spreads into the ventricles in a well-organized pattern. So the first spread is into and across the septum. And now the question is, why is this vector not like this? If we're spreading from here to here, why is this vector not like this? And it's a technicality. It's because the left bundle branch depolarizes before the right bundle branch, and the depolarization in the septum is actually from left to right. The depolarization in the muscle, which is the big signal, not the Purkinje fibers. Purkinje's fibers are small, septum muscle is big. The septum muscle contracts from left to right. Technicality. But it's an interesting technicality because it generates a vector like that, negative in lead 1, maybe almost hard to detect in lead ABF. In which, so negative in lead ABF, small positive in lead AB, I'm sorry, negative in lead 1, small positive in lead ABF. Which electrode would give the largest negative signal? Okay? ADL would be most anti-parallel to this vector. It's negative in lead 1, practically invisible in lead 2, so baseline in lead 2, positive in lead ABF, positive in lead 3, practically invisible to lead ABR. No?
Is there such a thing as being between ABR and lead 3 or?
Yeah, so if something were like this, if something were oriented like this, it would be between ABR and lead 3. And it would be positive in both ABR and lead 3. Okay, so septal depolarization generates the beginning of the QRS complex. The QRS complex overall represents ventricular depolarization, but the first step of ventricular depolarization is septal depolarization. What's the next step of depolarization? I told you this a few minutes ago. Septum, then what? Apex. Septum, then apex. The depolarization of the apical muscle generates a vector like that. So it's positive in lead 1 and positive in lead ABF. In what electrode is it most positive? In what electrode pair is apical depolarization most positive? Mike, or either Michael or Easton.
2.
Lead 2.
Yeah.
Once again, lead 2 is the one where it would give us the most positive signal. Which lead would give us the most negative signal? ADR. Lead 1 is going to be positive. ABF is positive because we're talking about a big signal now oriented in that direction. Positive in lead 1, positive in lead 2, positive in lead ABF, hard to see in lead 3, hard to see in lead ABL, negative in lead ABR. Why is this signal, apical depolarization, so much bigger than this signal, septal depolarization? The apex is bigger. The apex, this cartoon doesn't capture it, but the apex of the heart is much more muscular than the interventricular septum. So the spread of apical depolarization is a big signal. Big signal. After apical depolarization, what next? The free walls. The free walls depolarize. Why is it and it spreads from endocardium to epicardium. But why, so we've got free wall depolarization spreading here and here. Why is this dominating?
It has no muscles.
Yeah, the left ventricle is much more muscular than the right ventricle. So free wall depolarization generates a vector something like this. Positive in lead 1, negative in lead AVF. What would it be in lead AVL? Somebody shout out an answer. Positive, negative, or 0?
Positive.
Positive in lead AVL. Lead 1, positive. Lead 2, what would it be in lead 2? Negative, maybe smaller negative. Hard to tell. Lead AVF, negative. Lead 3, negative. Lead AVR, maybe hard to see. Negative.
How do you tell if it's negative or just hard to see? Like, because I feel,
How do you tell if it's negative or
or
what?
if it's just hard to see, like the difference between like
Oh,
two.
I'm just guessing.
Okay.
So, I mean, we're not going to get into the, fine measurements. I'm just eyeballing the fact that this vector is pretty close to perpendicular to this lead. I'm just doing it by eyeball. And that's all I'm going to expect you to be able to do. Did that answer your question?
Yeah, so if you were to test us on that and then we explain why we think it's like either perpendicular or not with this.
I'm not going to ask you for a subtle, so for example, I would not say, if I were to give you a question like this on a quiz or an exam,
It would be obvious.
it would be obvious. As if you know this, and you know the pattern of excitation in the heart, and you know which direction the vectors are, in your mind you can generate vectors, you can answer the question. And if you say small negative, when I would say no 0 because it's perpendicular, we're okay.
Okay.
But if you say large negative,
Then,
and I say perpendicular, we're not okay. Yeah. Natalie?
Lead 1 is positives, and why doesn't it go up?
It is still up. But free wall is smaller than apex. So the spread of this is a smaller vector than this. And so it is still, it's positive, but it's not as positive. And so it goes from a big positive to a smaller positive. Whereas here, it goes from a positive to an actual negative. Did that answer your question?
Yeah.
After the spread of ventricular depolarization, all of the ventricle is contracted. It's all depolarized. There's no vector. There's no spread of depolarization. And so the signal goes back to baseline. Between the QRS complex, which is the spread of depolarization, and the next signal, which is the spread of repolarization. The spread of repolarization is dominated by the apex, just like the spread of depolarization was. But it's not, repolarization spread is not just playing the tape in reverse. Remember, spread of depolarization went septum, apex, free wall. The spread of repolarization is outward to inward. And that generates a vector something like this. So this signal is positive in lead 1 and positive in lead AVF. It's small and spread out because repolarization is not as well organized as depolarization. Would this signal be positive in lead 2? Yes. Would this signal be positive in lead AVR? No. You're getting the hang of this. No.
Okay, well, hold on. So if the two ventricles are contracting at the same time,
Yes.
are we pumping blood from the right ventricle into the pulmonary artery at the same time as the left ventricle is pumping into the systemic circulation?
Yes.
Okay.
The question was, are we pumping blood from the left ventricle into the aorta at the same time that we're pumping blood from the right ventricle into the pulmonary circulation? And the answer is yes. Question? Yes.
For the AVM, or the repolarization, is it negative or hard to see?
For the what?
For the repolarization?
For the repolarization in AVL, repolarization in AVL would be hard to see. This vector, well, maybe it would be positive, but pretty small positive compared to lead 1 and lead 2. I'm not gonna test you on these subtle evaluations. I'm gonna test you on big differences. If you become a cardiologist, you have to get into the subtleties. So now you understand the electrocardiogram. You can see that in this patient, the QRS complex was big in lead 2, big in lead 3, small in lead 1. So let's see if we can figure this out. Well, you can figure this out as homework. The vector of apical depolarization, which is the biggest signal here, is big in lead 2, big in lead 3. Well, what's our prediction? What is it? Is it going to be big in lead AVF? Yeah. Is it going to be big in lead AVL? No. Is it going to be big in lead AVR? Well, it should be, but I covered it up. It should be big negative, biggish negative. So I'm not going to ask you to do this. Well, I'm not sure about the problem set. I can't remember if I asked you to do this, but comparing lead 2 and lead 3 and lead AVF tells you that this vector was, sort of something like that. Positive in lead 1, positive in lead 3, positive in lead AVF, positive in lead 2. We could get into the nitty-gritty, but that's what I would ask you to be able to evaluate from an ECG. So you're going to be working on this ECG as homework, or on the problem set. Let's do a few clickers together. Then we're going to take a break, and you will be able to work on at least starting to look at the questions of question 2. Once again, there is no question 3. You can work on questions 4 through 7. But let's do this together. And you have hard copies of these clickers on the very last page of your handout. So in the ECG, which of the following are true? Let's do this as a clicker. So show me your dig out your clicker and show me what you think is the best answer. Okay, I'm seeing a lot of, good. So when I stimulate your action, you come up with an answer. A and C are both correct. The best answer is both A and C. The P waves do represent the spread of atrial depolarization. They are normally positive in lead 2. They are usually invisible in lead AVR, or negative. They're large and negative in AVR. And they're seen in all leads. Okay, let's do the next one. Again, in the ECG, which of the following are true? Okay, show me your answers. Yeah, I think it's the same set, it's A and C again. The QRS complex is normally something like this. So it's positive in 1, 2 in AVF, it's negative in AVR, and it is seen in all the leads. It's the biggest signal, it's seen in all the leads. Okay, one more. Which of the following are true? I didn't teach you these, but I'm going to teach you now. I'm going to show you what your best guess is. Some of these I taught you and some of these I didn't teach you, but I want to see your best guess. And then we'll take a break. Okay, show me your best guess. I'm about to click forward. Best guess is that they're all true. So the T wave does represent the spread of ventricular repolarization. That's the definition that I gave. I said over there somewhere that the T wave represents the spread of repolarization from epicardium to endocardium, from outside to inside. So depolarization spreads from in to out, repolarization spreads from out to in. That's a true statement. The T wave is normally positive in lead 2. We did that one together. So let's look at an ECG. Ventricular systole is the period from the beginning of the QRS complex, the beginning of depolarization, to the end of the T wave, the end of repolarization. So the interval from QRS to the end of T is a good measure of the duration of ventricular systole. Remember, the duration of the QRS complex is a good measure of how fast it's depolarizing. But the interval from the beginning of the QRS to the end of the T wave is a measure of the duration of ventricular systole. We're not actually measuring contraction. This is an electrical representation of systole. Okay, let's take a break now. During this break, let's take a good long break. During this break, you can work on questions 2 through 7. And I can give guidance while I'm here. And we can then do this again. We will do this again in a breakout room on Zoom on Wednesday. But for now, let's spend some time working on questions 2 through 7. And then we'll start up with another lecture.